In this video, we are going to look at a very important class. This is a time complexity class called P. Okay, so P stands for polynomial time. It is the class of languages that are decidable in polynomial time on a deterministic single tape Turing machine. Okay, so in other words, okay, so we take a time-bound n to the k, so that it's a polynomial, and this k will start from 0 to infinity. From 0 to infinity. So of course, when k is equal to 0, time of 1 means it's a constant time. So any problem that can be solved in constant time, okay, will be n to the 0. So this is constant time. And then n to the 1's power, so this is linear time. And then this is quadratic time. And n cube is a qubit time. Okay, so and in general, any problem that can be solved in polynomial time is considered efficient. Okay, so it's considered tractable because in practice we often have a polynomial time computable problems with time complexity in a lower degree of polynomial, for instance, linear time or quasi-linear time, n log n, which is very close to linear, quadratic, qubit, and most of the polynomial time algorithms would run in time less than or equal to qubit time. Okay, so that's in practice, and hence we use polynomial time to indicate that a problem is efficient, and we call it tractable. A problem is tractable means that there is a polynomial time algorithm deciding it. Okay, then polynomial time algorithms are considered efficient algorithms for the reasons that in practice, almost all the polynomial time algorithms we have encountered are in polynomials of lower degrees, such as linear, quasi-linear, quadratic, and qubit time. Okay, so there is another thing that there is another thing about polynomials, is that polynomials are closed under addition and multiplication, and also polynomials are closed under composition. So in other words, if I have a polynomial p of x and another polynomial q of x, then we know that p, maybe I should start a new whiteboard. Okay, so polynomials have the following good properties. In addition to that, practical efficient algorithms are in polynomial times with a lower degree of polynomials. Okay, so polynomials have the following nice properties. Okay, so one is that its polynomials are closed on the addition and multiplications. So in other words, if P of X and Q of X are polynomials, then P of X plus Q of X and P of X times Q of X are also polynomials. And the second, polynomials are closed under composition. So in other words, if P and Q are polynomials, then replacing X by Q of X, this is also a polynomial. Okay, so here P, Q are polynomial. So that is a second property. And the third property is that polynomials well, really, that's for time complexity. We just need these two properties. Okay, so other properties are nice in their own right, and they have applications in other areas, but not as a time bound. For instance, polynomials can be represented by coefficients as a string. Okay, so coefficient representation. So let me just, since they are not, since this property is irrelevant to what we are concerned here, so let me just not worry about it. Okay, so now let's move back. All right. So now let's look at our bullets. So in practice, all efficient algorithms each has a worst case running time bounded above by a low degree polynomial. As I said earlier, either linear time, quasi-linear, square time, quadratic time, and cubic time. So for quadratic time, sometimes you will have n squared times log n, right? So that's also possible. Okay, while a running time of a polynomial of a high degree cannot be efficient, such as a very, very high degree polynomial like a million, right? N to the 1 million power. So that is not efficient at all, but it is still much faster than exponential time asymptotically because as we said, as we saw in the previous video, we know that even you have n to the, say, a big number, 1 million, it is still asymptotically a small o of 2 to the n, right? So it is still efficient in that regard, but of course, in practice, as we know that all polynomial time algorithms all tend to have time bound with a low degree polynomial. And then I just mentioned polynomials are closed under common operations, addition, multiplication, and composition. So these are good enough for using polynomials as a measure, as a time measure. And P is a variant. So this class P, which is a set of all languages that has a polynomial time that can be computed by a deterministic decider in polynomial time, which is just this. Okay, so once again, that's the definition. So P is a variant for all models of computation that are polynomially equivalent to the simplest Turing machine, namely the deterministic single tape. This is the third nice properties. So, but again, for it basically just means that no matter what computation models we use, now remember that if you have multiple tape or two-dimensional tape, so any model that can always be converted to that's always equivalent. Okay, equivalent means that if a language is accepted by a model, computation model, like Turing machines with two-dimensional tapes, that kind of thing, that it is equivalent to, it is accepted by a Turing machine with a single tape within polynomial time bound. So which means that, say, if you run into, so let me start a screen to look at this property 3. Okay, so say if L can be is accepted by a deterministic Turing machine with let's say a K tape or with K tapes, then there is L subsetted by database K tapes in time. So let me put it in time here. In time T of n. Okay, so it's a number of steps, right? So you have an input of length n, you run this Turing machine with K tapes, and it gives an answer in time T of n. So let L, if L is computed by the DTM with k tapes in time t of n, then L can be accepted by, well, then there is, let me put it this way, then there is a polynomial, let's call it Px, such that L can be accepted by a DDM in P of T of n steps. Okay, so that means that within polynomial time bound or within polynomials, so let me just, so within polynomial time bound, or computation models can be simulated by deterministic Turing machine with a single one-sided tape. Okay. Let me just say, let me rewrite this. Let me rewrite this, okay. Yeah, my the iPad doesn't have a good eraser, so it can only erase like this. Okay. So in other words, so let me just say, if a problem can be computed in time T of n by a computation model, then let's call it L. Then L can be then there is, okay. Then there is a polynomial P of x such that L can be computed by a single tape by a single tape deterministic Turing machine. So this is also called extended church Turing thesis, because when we talk about church Turing thesis, at that time we just say that any computation models are not more powerful than one tape or single tape deterministic Turing machine. Okay, so now we can further, after we have this time measure, we can further stipulate that they are equivalent within a polynomial time bound. So this can be, okay, oh, forgot this, in P of T of n time. Okay, and polynomials have other nice properties, and some of those are used in cryptography. But we're not dealing with cryptography, so these three properties and give us a good reasons to look at polynomial time bound and define a complexity class called P, which will be the ones we consider as efficient or tractable problems. So any problems in P are tractable, and any tractable problems are in P. So that's what our consensus, even though a very high degree polynomials, an algorithm with a very high degree polynomials are not efficient at all, but asymptotically it is still faster, much faster than exponential time. Okay, and the good thing about polynomials is that in practice, almost all algorithms that have polynomial time are indeed in polynomial times of low degrees. How low? Well, linear, quasi-linear, quadratic. Quasi-linear means n times log n, big O of n times log n. Quadratic and qubit, that kind of stuff. All right. Okay. Now, when we do a measure, we do need to encode the description of a problem. Okay, so that means that inputs and outputs need to be encoded over a fixed alphabet. In general, we use a binary alphabet for a computing device to recognize. Okay, so we do need a fixed encoding to describe the problem, just like a description of a Turing machine. Once again, whenever we mention Turing machines, we should have in our mind that a Turing machine is just a program. Okay. So any natural encoding of the same problem should be polynomially equivalent. Namely, let E1 and E2 be two encodings of the same input. They are polynomially equivalent if they can be transformed from each other in polynomial time with polynomials P and Q, such that the size of E1 is bounded above by P of the size of E2, and the size of E2 is bounded above by Q of the size of E1. Okay, so this is within polynomial time bound, they are equivalent. Okay, so this is So this is true, right? So almost any natural encoding, we will have this property. However, if we use, I'm sorry, so let me just finish this bullet first. So encoding is customarily denoted by, so a left angle property, I'm sorry, angle, the left angle and the right angle brackets. Okay, so we have seen this when we look at the encoding of Turing machine. Okay, so familiar encoding methods for graphs, automata, and the like are all reasonable. For instance, we can use ASCII code, we can use Unicode, or we can, so after that, if you have several components, two components, so you have a set two components, just like we did earlier. So if you have a encoding of M followed by X, so then we don't need to encode X, we just need to encode M using a concise encoding method. Okay, so that will have the size of it under that encoding is just a constant, because M is a constant, plus the length of X. Okay. But if you use a unary notation for encoding numbers, then we don't have this property. We don't have this, okay? Because using unary, then we have this exponentially larger, okay? So for instance, let's say we take a number 17, so then the unary string is 1 to the 17, so the size of it is 17. Now remember, 17, if to represent 17, you only need 5 digits instead of 17. Okay, so likewise, if you have a big, let's say 1,000 to the 10, right? So the size to represent any number below 1,000, you only need 10 digits. But then, of course, so 2 to the 10 and 10, this is exponentially more than 2 to the 10 is exponentially larger than 10. Okay. So once again, this is about fixed encoding. So now let's look at a few, some examples of problems in P. I'm sure you have already looked at problems that are in P, such as the data structures you learned, then the operations such as push an item to the stack, or push an item to the queue. Of course, putting to the queue, they have to run in linear time. You have to look at the size of the queue, but if it's doing on a stack and you don't care about the size of the stack, because the pushing and pop are always operated on one end, so that only requires constant time. So the designing efficient algorithms for solving a particular problem. So in most cases, it simply means that we want to devise a polynomial time algorithm. Okay, so sorting is polynomial time, right? So if the insertion sort is n squared, big O of n squared, we look at merge sort, heap sort, right? So even binary search tree with a then a merge sort is big O over n log n, right? So if a binary search tree which is well balanced, like an AVL tree using AVL, then this is still also in the order of n log n. So today we're going to see 3 problems in the setting of decidable languages that are in P. So that means that we will represent a problem in the form of a language. So now we define the first example here. We defined a language called path. Okay, so which is a encoding of this 3 tuple. So you have a graph G, you have a start node S, and you also have a target node T. Here, G is a digraph, meaning it's a directed graph with a path from S to T. So we put all such instances together and we call it path. So in other words, an instance here is that you have a graph, you have a designated node as a start node S, you have a designated node as a target node T. And G here, this graph is a directed, and then this tuple, 3 tuple belongs to path if there is a path on G from S to T. So we want to show that this problem is in P. So here's a proof. So what we do is we just need to conduct a breadth first search starting from S, okay? So what it means here is that, so it's starting from S, and then you look at the graph. Now this is a digraph, so from S. So then this is, all the nodes will be here. So that is the first level. If T is one of these, then we are done. We found a path, so then this GST belongs to path. So if not done yet, then we'll keep on doing. Any moment that T is found, then I have found that path. Okay, so so when you can stop here, now this is a breadth first search, which means that if some of the nodes have already been searched before, then you don't have to generate it. Okay. So all of these nodes are not generated before. And so what would be the height of this tree? So the height would be at most the number of nodes. Okay, so that's it. So that means that we just need to do a breadth first search. Then we can do this at most, right? At most n squared time. Then we can so n here is a number of nodes. Okay, so then we can determine whether a given instance GST belongs to path, whether there is a path from S to T on G. Okay, so this is straightforward. So the next one is called relative prime, which is a language name, so in here, it is a set of encodings of X and Y. X and Y are integers and they are relatively prime. Then we'll say REL prime is in P. So the proof is to use the Euclidean algorithm to compute the greatest common divisor, GCD of X and Y. So repeat the following until Y becomes 0. So we say X to Y mod, X So we compute x mod y and assign the new value again to x. Then we swap x and y, output x. Okay, just a repeat. So we just swap x and y and then assign. So we do the same thing. So they keep on doing it until y becomes 0. Okay. So if the result, so then we output x. If the result is 1, accept, otherwise reject. Okay, so 1 just means that GCD of x and y is 1. Now this is a Euclidean distance. You should have been already seen it in discrete math. Okay, or well, probably in discrete math. That you should have already seen it. So the running time here is the maximum, is a square, is a quadratic of the maximum of the length of the maximum value of x and y. Okay, so here, so in order to see y is a quadratic time, so we know that a modular operation takes, now this is of course a fast exponential. We don't need fast exponentiation, so we just need a modular operation. So that only takes the order of the size of x, which is big O over log x time, and each modular operation reduces the time of a number by half. Okay, so hence there are at most log n rounds of operations. So this is a polynomial time. So you only have this many rounds, and each round, okay, so what you do is you take the modular operation, which is log x, and then swap x and y. So it's a polynomial. So next we're going to see another example. So we let L be a context-free language, then L is in P. So in other words, we can determine whether a given language is we can select, so we can determine whether x on a whether x of a given instance, right? So x is in L or not. So this is in P. Okay, so why this is in P? So we have already showed that each sentence x of length n in L can be derived in 2n minus 1 steps from a context-free grammar G in Chomsky normal form. So let me refresh our mind and why this is the case. Okay. So first of all, in Chomsky normal form, what you have is in this. The production rules in this form. Okay, and then this A is a symbol, B is a variable, C is a variable, and A is not epsilon if A is not X, is not a star symbol. Otherwise, it could go to epsilon, and S is a star symbol. So then, of course, you start. So let's say you have a string X with length n. So what we want to derive here is that you start from S, and then to see this string can be derived. Okay, and using this form, we can just so this tree here, if it's so this is a binary tree, but then we have a length of n. So what you are going to do is is look for whether there is a generation tree, derivation tree that derives this x. Okay, so in that tree, well, again, it's a binary tree. So how many steps we can determine? So the derivation height. So the height of it is 2n minus 1. So you start from s. It's equivalent to generate so a sequence of length n of variables. Okay, so actually 2n minus 1. And then we just plug it in with a special, with a symbol to see whether it's equal to the given x. So it is, so once you have a derivation tree, I just need 2n minus 1 steps, and I can determine whether a given x can be derived from this derivation tree. However, how many derivation trees there might be? So that is a huge number. So using brute force is obviously not going to give the results for us that we want. As a matter of fact, this is a very big, the number of derivation tree is big, okay? So in particular, we let C of n denote the number of derivation trees. Then occurs for a sentence for the string of n symbols, called a sentence or a string, right? So this is the terminals, the string of terminal symbols. Okay, so then it can be so it can be considered as we first generate a partial sentence of length k, and then generate the remaining partial sentence of length n minus k. So the number of such trees will be equal to C of k times C of n minus k, and k here starts from 1 and ends at n minus 1, and such a number is called a Catalan number, which is equal to 2 to the n factorial over n plus 1 factorial times n factorial. Okay, so if you really want to get an idea of how big is C of n is, then you can see that this is a huge. Okay, so quadratic. Now, this is so you may have. So it's easy to see that n squared is at least n to the n over 2. So that is really a big number. Okay, big. Okay, so obviously we cannot just look at or exhaust or brute force or possible derivation trees. Instead, we are going to use dynamic programming. So a dynamic programming algorithm is the following. So we'll come up with a recurrence relation. So let me start a whiteboard again. Okay. Dynamic programming. So it involves, the first part is to find a recurrence relation. Recurrence relation, then solve this using memorization. Solve it using memorization. The good thing about this is without the need of recomputing the same subproblems. Okay, so that saves time, and as a matter of fact, for this problem, it's going to be in running time. So what is the recurrence relation? So we need to create a name for it. Okay, so let's look at what we can do here. So we want to come up with a recurrence relation. So we come up with a name to describe the problem. So which is D of A comma I J, which is a Boolean variable. Here, A is a variable and J greater than I, such that D of Aij is true if and only if substring xij can be derived from A. So what that means here is, say you have a string, and this is xi to sj. Okay, so it's S0, and then let's say it's length n. So we let D of A comma ij be a Boolean variable where A is in V, j greater than I, such that this Boolean variable is true if and only if a substring. So let's think of this. So this is x, and this is I. This is k. So let me just, what we are looking at. Okay, so what we want to determine is whether S1n belongs to, this is a, so we really want to compute this because this represents the string x itself, so from the first one to the last. Okay, and so maybe we can say start from x1 instead of x0. So then the number of time, now using memorization means that I'm going to start from the bottom, even though I have a recursive call, because recursive call you have to keep on doing until you see the boundary condition, then you work your way back. So this is called backtracking. Okay, so then, but if you, as long as we memorize solutions to subproblems, then this problem can be solved in terms, the runtime is in terms of the number of subproblems, okay, and the dependencies, okay. So as you can see here, this only depends on 2 subproblems, okay. One is for each of these rules, A, arrow, B, C, I want to see whether my input string X can be divided into 2 parts. The first part can be derived from B, the second part can be derived from C. Okay, so in this case, that the running time is really in big O of n squared times 2, because now I have, for each step, I have to look at, I'm sorry, not times 2, here. Okay, I and j, so it starts from 1 to n, so this is, the dependency is not 2, it's just, so if you look at this ij, it depends on j minus I many, or plus 1, many subproblems, and begin with is n minus 1 plus 1 is n subproblems. Okay, so that's a qubit time, because the dependency times the number of subproblems, that's n qubit. So that is dynamic programming. So then that's it. So that is so we look at 3 examples that are in P, and then the last one we use dynamic programming. So once again, dynamic programming is just to try to come up with a good recurrence relation for solving the underlying problem. And then you use a memorization to, so this is a process, right? So because you have a recurrence relation when you want to solve it, it will go down to the boundary condition, and then you work your way back, okay, backtracking. So in order to avoid computing the same problem multiple times, and then what we need to do is to store the result the first time that particular subproblem is encountered. So that way, next time when we need to get the result of another subproblem, we just need to do a table lookup in one step instead of carrying out a recurrence relation and then that expand to a subtree. So that will take exponential time to do this. Okay, so that's the end of this video.